Okay, we're back. We're live. 1 o'clock rock. I'm Jay Fidel. This is Research in Manoa, which is a program we do every Monday with the help of the SOEST, the School of Ocean, Earth Science and Technology, and also HIGP, the Hawaii Institute of Geophysics and Planetology, and CMOR, the Center for Microbial Oceanography Research and Learning. So it's great to have contact with the university, to be supported by the university, and to have guys like you come around. Sure. Paul Wessel, professor of Geology and Geophysics in SOEST at UH Manoa. Thank you very much for coming.
Oh, thanks for having me. It's fun.
Yeah, so we want to find out who you are.
Yes.
Okay.
Well, my name is Paul Wessel. I am a citizen of Norway and a resident, and a permanent resident of the United States. Yes.
Norway.
So
wow.
I came a long way. It's a nice weather here compared to Norway. We have some issues with snow and temperatures. So yeah.
Is it getting worse in Norway?
No, I think it's getting warmer.
Is that right? Okay.
Global trend.
Sure.
Global warming. Yeah. So snow's melting, at least compared to when I was a kid. So I got my bachelor and master's degree in University of Oslo, geology and geophysics. And my advisor thought I should go abroad, broaden my horizons. So I ended up in New York at the Columbia University, the Lamont Doherty Earth Observatory. Did a PhD there, kept moving west and south, ended up here as a postdoc. And in '91, I became an assistant professor and sort of worked up the grades ever since.
That was, let me see, that's 25 years ago.
Yeah, it's been there a long time. Lived here longer than anywhere else in the world.
Yeah. Well, so why?
Yeah, it's a good question. When I first started, I actually had no plan. Finishing high school, go to college, just go to college. I had no specific plans. But during the first year, we all got this letter saying, hey, the North Sea oil boom is starting up. And there will be all these great jobs in geology and geophysics. And if you sign up for this petroleum geology program, you'll get huge salaries forever and life will be good. So I said, sounded good to me. Yeah. So I signed up, and after a year and a half, I realized, wait a minute, I was fairly good at math and physics, and there was a lot of geology and bugs and sediments and things. So I ended up talking to an advisor and switching to applied geophysics. Then I got into more geophysics and computer science and applied computational solutions to problems, and just sort of one thing led to the other. So my thing was that I really enjoyed working on science problems, but solving them with computer technology and software, and writing the software to do the problem.
And during the past 25 years, a lot has happened in that department.
Yes. I missed the punch cards, but I just got in just after that.
You didn't need the punch card. It's okay.
That sounds horrible. Yes.
So, did you get good grades?
Yeah, I was a pretty good student, although I was a lazy student. So I was doing okay without working too hard, which is a bad thing. But
more and more it revealed that if you just traveled west and kept your mind on the same subject, it would work out. Even though I'm sure that in this period, since you originally made the decision way back when, it's all changed. I mean, it's just evolved into something that no one would have predicted when you first started.
Oh, absolutely. I mean, I remember my first geology class was, I think, in high school, so that might have been 1975, and this is like 10 years after the plate tectonic revolution that revolutionized our understanding of how the Earth works. And that still hadn't made it into the textbooks I was operating with back in my home country. Yeah. So it takes that long sometimes. So yes, that's been changed.
Would you say in this period, I'm just ruminating with you here, but would you say in this period the world, especially academia, has become more conscious of ocean and earth science and geology and physics and all that? I mean, because I mean, it's really telling that you say this enormous change happened in what I guess geophysics,
right.
and it wasn't in the textbooks 15 years later.
Right.
It's like nobody was paying attention. The educational system really wasn't connected.
Well, this is a different era, so things took longer to propagate through, obviously, with media and stuff. So there was that, but Norway was a smaller country. They didn't have that tradition of doing a lot of academic research in this area. So at high school, this book was in Norwegian, so this was produced in Norway by scientists who did this work. So on the global stage, it took less time for this information to propagate into textbooks and university curriculum and so on. So
how about now?
Oh, yeah.
Now it's right away.
Yeah, it's standard. It's the paradigm that all of Earth science is built on top of. So
I had lunch one time with the vice mayor of Beijing.
Goodness.
Yeah, I didn't realize exactly who I was dealing with. And I said, Mr. Vice Mayor, whatever you say to somebody like that, Mr. Vice Mayor, it's wonderful that, 29% of your college graduates have specialized in engineering. And he said, yes, it is, except you're wrong. It's not 29%, it's 59% of our college graduates have specialized in engineering. And it seems to me, when I went to school, which was in the 50s and the 60s,
Right.
Science was really for a small percentage of people. Most people were in liberal arts. Maybe it was the nature of the school,
Sure.
But it strikes me that at least in China, they figured out that it's better for the society in general to have more scientists, more engineers. Are we doing that?
We're trying. There's all this initiative about STEM education. We clearly need people who can do science and engineering and technology. But those are hard subjects usually, and they're not always taught well. It's a hard subject to teach also, and we don't always focus on how we teach, but there's a revolution on the ways there too. So I think there are positive signs. You've got to get the kids hooked early. People are doing that, of course, with science fairs and shows like this and shows for kids. So there's more stuff out there, but there's also more distractions, obviously.
Yeah,
there's just more of
we live in
everything.
a world of distractions.
Yeah, so when I grew up, there was, we had nothing. We had one channel on the TV and out climbing trees. I mean, it was
Black and white.
life was simple. Yes, black and white too. So life was simple, and now because you have cell phones and web pages and everything, so it's much harder to organize your thinking, I think, and spend time on what matters. It's just.
What about the students? You're teaching, I'm sure, by virtue of your title. Have you noticed a change in the students? Are they more ardent about science? Are they more interested? Are they more committed to a career of science?
I think they know more in general about science because they've been inundated with TV shows and media in general. So I think they heard more things. In the old days, you sort of had to seek it out. And now I think it comes to you a little bit more if you're willing to listen.
Yeah.
I'm not sure if they're more into science or not, but they seem to be more aware of it, I would say.
Do your students, are they dedicated to, geology and geophysics, or are they come from the English department?
No, it depends. I mean, for the introductory courses, the 100-level courses that satisfy the science requirements of any liberal arts major, they will get all walks of life. Mm-hmm. And some of them just want an easy science credit, and they hope geology will be easy.
How long they are.
Well, it's okay. We don't want to make it super hard. We want them to be attracted to it because it covers so many topics that are fundamentally important to everybody living on this planet. Sure. And this is the last science class many of them will ever see. So it's important to get some words out.
Yeah. This may be the last few years of the planet, too.
Might
as well enjoy it.
Yeah, that's true. Right, so there's that. But the students some get hooked, others have decided already, and they trickle in to become majors. And those are, of course, dedicated. This is what they want to do. Yeah. They're attracted for all kinds of reasons, working outside, volcanoes, ocean, you name beaches, whatever, and they get very excited about geology and geophysics, and they come to us.
Working outside. I find a lot of people who sit in that chair on Monday at noon are working outside.
Same thing. Yes, it's nice. Well, I must say, I'm more a computer jockey, so they chain me to my desk, and I sit inside of a very frigid air-conditioned office in the post building. It's nothing like here today.
So you're a professor, and
I'm
you're
a professor.
teaching them. And you mentioned earlier that teaching science, has perhaps greater challenges than teaching liberal arts courses, and I can see that. But what's the secret sauce that you have to teach these polyglot classes, because some are committed and maybe others are not? Well, how do you do it in a way that that makes them more committed?
Right. Well, it's not just for science. It's engaging the student and have a conversation with them and have them think and not passively take notes from what the professor lectures. I mean, we all had classes like that where you show up, there's 400 of you, person is droning away on the blackboard, and you take notes as fast as you can, and you can't.
Hate that.
And, you lose a lot. You just get a little bit out of that unless you're very smart and prepared, and then you get more.
Yeah.
So this mode of teaching now is much more interactive, asking students. Students have to work on groups, come back to you with the answers, and trying to get the wrong answer sometimes too, because you learn a lot by failure.
Use that as a discussion point.
Yes. Yeah. So coming up with why isn't this the right answer? That gets them thinking a little bit. So
is this just you, or is this UH in general?
No, it's teaching in general, I'd say, in college level particularly. There's been a lot of studies about why do undergraduates drop out and they can't handle this material. And a lot of it is we kept this teaching model for forever, 400 years.
Yeah.
And it's just now starting to realize that we should
that's
actually
good.
do it differently. We were lucky to have a professor and Nobel laureate in physics here visiting last week and talk about, he's been doing a lot of studies on how you teach, the science of teaching, what works.
Yeah.
And all those things I just mentioned about interactive, active learning, engage the students in problem solving, all this stuff. You can do tests and measure, and that actually measures much higher in terms of retention. So it's clear that you've got to do something like this.
So how does this mesh with the MOOCs phenomenon? You know,
Yeah.
which UH is not heavily involved in MOOCs. Other schools
That's
are.
true. That's true.
And there's not a lot of engagement. I guess there is some engagement in MOOCs. You know, you talk to your classmates, wherever they may be.
Yeah,
But
yeah.
where do you fit MOOCs in the landscape of the modern teaching approach?
Well, it certainly lowers the barrier of entry. You know, you can do it from your home, wherever you are. The access is certainly a huge, it's huge benefit in just terms of access. But I'm not an expert on MOOCs at all, but most of them seem to be fairly, they disseminate information, and the students are not always able to feed back in. And this is a limiting problem. If you have 1,000 people watching something, how can you possibly allow for a lot of discussion and feedback one-on-one and so on? So there are some limits to that, but certainly it's way better than getting a book and reading the book for yourself.
Yeah,
you get
because it
something.
demands a certain amount of
Yeah.
engagement,
Yeah.
even if it's not as much as a classroom setting.
Yeah.
Well,
So
before we take a break on this, I would like to get into your science.
Mhm.
This is you as a researcher.
Yep.
I guess you talk about it in class, but your primary research, what is it?
I'd say plate tectonics and interplate volcanism on a global scale. So I study how the Earth's surface plates move relative to each other and relative to the deep mantle. So the Earth is split into, typically we say, a dozen pieces that are jostling around. Number change with times, depending what period you're looking at. And whenever these plates move past each other or towards each other, bad things happen, like earthquakes, volcanoes, tsunamis. So we want to study not only how the plates are moving today, which we can see directly with, where are the earthquakes, the ring of fire, that sort of stuff, but also back in time to understand how did the Earth evolve? How did it get to where it is now? And why are these features there that look passive and old? So trying to study, basically play the movie backwards and see what the surface looked like as you scroll to the left on the times handle. How far back can we go to get a sense of where these pieces came from?
Yeah.
So that's sort of one aspect of my research.
Yeah. So what's the trend on it? I mean, was Earth, in terms of geologically speaking, with all those moving plates and whatnot, and all the heat in the mantle and the way the whole thing breathes, was it more active before? Is it more active now? Will it be more active or less active in the future?
So the Earth is dying, sorry to say. It takes a very long time. But
I heard that on here on ThinkTech, and put this in your notes. This is going to be on the final exam.
That's right. I wouldn't rush out to buy spam and water right yet. But
Toilet paper.
Toilet paper. Those are the two things. No, the Earth is losing heat. It's generating heat from radioactive decay too. But eventually, all that will go away, and the Earth will become cold and stiff and all those things. But that's so far in the future that I don't even have a number to
But
give you.
that evolution does suggest that the Earth is a better place if it's active geologically. Am I right?
Yeah. Oh, I agree. It's more exciting to go and see volcanoes than a barren, Martian landscape with no water.
For entertainment, anyway.
For instance, yeah. So the Earth was more active in the past. There was more heat. There was more energy. But it's hard for us to tell exactly what the surface of the Earth looked like in the past because plate tectonics tends to consume what's on the surface and you recycle. So we can only sort of reconstruct with great confidence the last 200 million years of Earth history, which is just a little sliver of the 4.6. You can use some other techniques to get back maybe 1 billion, and then it gets iffy what the Earth looked like, and we don't really know. But it probably wasn't plate tectonic all the way back to the beginning. It was probably some initial stages where we had a lot of volcanic eruptions and no organized plates yet. That came sort of later.
Okay, well, there's a question that's been brewing in my head for a long time, and that is, so you have the Earth, Mother Earth, changing, evolving, breathing, with all the processes in the plates and the mantle and all this. And then you have climate change, and that's changing things, in the air and on the surface, in the ocean, in the weather, And my question to you, and I'm not going to ask you this question until right after the break, but my question to you will be, it's a cliffhanger, is what's the
Google the answer,
relationship, if you can, the relationship between climate change and this geological evolution that we're talking about.
Okay.
We take 1 minute off. He knows the answer already, but he's going to tell you the answer after the break.
Cool.
Aloha! Hello, my name is Patrick Bratton. I'm host at Global Connections here at ThinkTech Hawaii. We broadcast live every Thursday at 1 p.m. We bring Hawaii to the world and the world to Hawaii, talking about international events and various things of interest to the audience. Please join me. I look forward to talking with you and having you get to meet some of my guests. Aloha.
Aloha, namaskar, and hello. My name is Anu Hittel, and I host the show called Climate Change Beyond Outrage. We go beyond outrage to find solutions to climate problems facing people, nations, and the world. I hope you will join me here every Tuesday at 1 o'clock. We broadcast live from thinktechhawaii.com. Aloha and bye-bye.
Hi, I'm Ethan Allen, host of Likeable Science on ThinkTech Hawaii. Come join us every Friday at 2 p.m. when I interview interesting scientists about what they do, why they do it, and why we should all care about it. It's a lot of fun to see. And you can learn interesting stuff. You'll hear all kinds of fascinating science, and we know you'll have a great time. Hope to see you then. Bye-bye.
Okay, we're back. We're live. We're here with Dr. Paul Wessel, Professor Geology and Geophysics at SOEST, the School of Ocean, Earth Science and Technology at UH Manoa. We're talking here on the show Research in Manoa, and we're talking about seamounts, detecting seamounts from space.
Yep.
Okay, that's what we're going on this.
Yes.
So, but first you have to answer my question.
The question was, how does the climate change and the long-term evolution of the Earth hook together? Well, very different timescales. So what I do, the plate tectonics, does actually affect the climate, but at the 10 to 20 million year time scale. So most people wouldn't care
That's
that.
different.
Yeah, so we're, right now we're zipping away on Hawaii towards Japan at the rate of a few inches per year. And by the time we all are dead, we haven't moved very far. So the climate's not going to change due to that.
Yeah.
But the climate might change due to melting of glaciers and weather patterns changing over time. So different things that affect the climate. Basically.
So all the sturm and the drang on the surface, with the weather,
Yeah.
does that have any effect, with the geological changes inside? And vice versa, do the geological changes inside have any effect on climate change and the weather?
That's a good question. So start first with the effect on the Earth. So more vigorous weather with more rainfall will lead to more erosion than normal. But we're talking about probably relatively insignificant amounts in terms of geologic change.
Yes.
If you sustain a very different climate for a very long time, yeah, maybe you will get higher erosion rates over time, more sediments get deposited. But for that to feed back into the driving engine of the Earth, no. The Earth is driven by its internal heat, and it doesn't get heated up by the sun or anything like that. It's just internal primordial heat from when the Earth formed way back, and also a radioactive decay that heats up the Earth. So Earth has to get rid of this heat. It doesn't matter whether the weather is hot or cold or the climate changes, really. So that's sort of fairly distinctly different.
I know it's not very comforting, but to some degree that is comforting to hear.
Yes, the Earth probably won't care. That part of the Earth won't care.
Yeah.
We might care, but the surface might be a little bit different.
So let's go to seamounts.
Seamounts, yeah.
So you talked about tectonic plates and the movement, and that really is fascinating, especially when you realize that the movement causes earthquakes and tsunamis and whatnot.
Yep.
What is a seamount in that landscape?
Yeah, it's good. So seamount is basically a volcanic island that didn't make it to sea level. So we're sitting on seamounts that broke the sea surface and built islands. There's no real difference between those and the ones that didn't actually make it across the sea surface. So the oceans are littered with these features, and they range from features that are very close to breaking the sea surface but never made it, to tiny little bumps. So
Did they ever make it and then not make it later? I mean, like for Atlantis, for example,
and
Atlantis.
sink away and drown.
Yeah.
Yeah, sure. Yeah.
They come, they go.
Yeah, all these islands here we are right now is going to eventually drown.
My God.
We can just look up the chain, past Kauai. You'll see that there's a ring, it's a line of seamounts, the Hawaiian Ridge, going all the way up about 3,000 miles, and then it makes a sharp turn going north, and that's the Emperor Seamount chain.
Yeah.
It's all been formed by the same heat in the mantle that's beneath the Big Island right now. Pushing up heat and producing new volcanoes, and the plate is moving over it, and it sort of carries like a conveyor belt these older seamounts away and building new ones. So that keeps going, and as the plate ages, the depth of the ocean at that point increases. The plate cools off and gets thicker and denser, and it sinks. So if you built a seamount that is, let's say, 3 miles, and it sinks down half a mile, then it may drown, right, with time.
Does the real estate industry know this?
Not sure.
I don't think so.
Yeah, they have to do
so.
long-term
They should
planning,
do-
though.
Yeah, right.
Yeah,
When
there's
they
something
say
there.
fee simple, it's not forever.
That's right. That's not forever. That's right. Lifetime is a good word for that. So
Okay.
it goes away. The volcanoes that do reach the sea surface, we get fringing reefs on them if they're in the tropics, and the reef will try to keep track of and keep up with the sinking, basically.
Yeah.
And they do a good job, but sometimes the seamount will be moved by the plate motions too far north, so corals don't grow as fast,
Yeah.
and the latitude gets higher, and then they just say, we give up, and they drown, and the thing just drowns.
So you're looking at seamounts as one, expression of the plate?
Yes.
Or the dynamics of the plate,
Yeah,
anyway.
two things that are important. One is just the sheer volume of volcanism. It's not all produced at the mid-ocean ridge or on the Big Island, for instance. It's everywhere.
It's
so how
everywhere,
much is it?
everywhere.
Do you want to tally it up?
Everywhere in the world, or just everywhere in the Pacific?
Everywhere on the oceanic lithosphere. So every ocean, basically. There's more in
Including the
Pacific.
Atlantic.
Yeah, all the oceans.
How about Arctic and Antarctic?
Yeah, there's less there, and it's interesting, why are there less there? Certainly the vigor of the convection beneath, maybe less. Plates are moving slower, might be something there, but we don't really know why there aren't lots of volcanoes under Greenland, for instance.
In a cold place like the Arctic or the Antarctic, is the hot mantle further in? Is it
No,
not
it's-
as close to the surface?
No, I don't think so. That's just a skin effect of the upper little bit. But
Okay.
we have active volcanism in Antarctica, Mount Erebus. It's erupting
yeah,
under
okay.
ice most of the time. So it doesn't care.
Okay.
It just, the surface might have to deal with
But
this.
Hawaii is a good place to study
Hawaii is a
this.
good place.
Why?
You can work. Well, there's the Hawaii Emperor chain that I spoke about, and the plate tectonic aspect of that is the orientation and the geometry and the ages of these seamounts along that ridge is clues for us to understand how did the plate move back in time then. So if it had these jogs, it must have done that back in time, perhaps, unless this plume that feeds the volcanoes didn't stay still or it moved. So right now, there's a lot of discussion about to what extent did this plume that feeding us from all the way down to the core mantle boundary, 2,900 kilometers up to the surface, maybe that thing is not still and vertical, maybe it blows in the mantle wind, and that's going to affect what you see on the surface. You can have a plate moving steadily in one direction, and the thing is blowing like this. You're going to get this zigzag seamount
Should
chain.
it always work in 2 dimensions like that, or is that just sometimes?
2 dimensions.
I mean,
Oh.
an X and a Y axis. In other words, it's moving this way, but it's also moving
Oh, it can
this way.
move any in 3D, yeah.
Yeah.
So think of it like a candle that's blowing in the wind. a
All
little
like
bit.
that. It's never a straight line.
No, I don't think so.
Life is not a straight
Yes,
line.
yeah, that's not a crack.
And
That's what I mean,
geology is not a straight
so
line
a 2D
either.
thing would be a crack. So
Yeah.
if you had a crack in the earth and plates moved apart, you have a mid-ocean ridge, and we have 40,000 kilometers of mid-ocean ridges on the planet, and there you produce volcanism steadily all the time to fill in the crack in the
Yeah.
void.
So
yeah.
your science is
Mm.
trying to get a bead on what these seamounts are doing.
Yeah.
Their dynamic, their movement in one way or the other, the
Mm-hmm.
speed of it, and I guess trying to predict where they're going and how fast and where they're going to go.
Yeah, so we're using these seamounts as markers for plate motion back in time, right? So that's one aspect of it.
Seamount is I love this.
Yeah.
Seamount is a marker for plate motion.
Right, yeah, so you can-
Seamount is a marker for plate motion.
So if you had the luxury of buying a very fancy time machine, let's say you could do that, you can go back in time and put a big X on a certain seamount and then
Yeah.
zip forward and you see that, oh, it's moved over here.
Yeah.
And we can measure this distance and we
Yeah.
can figure out how fast the plate is moving, and it's moving a few inches.
Because every seaman has a different look to it. It's like facial recognition.
Yeah, well, it
You
gets
know the
older.
design of it so that you
Yeah.
can figure it out. It
Yes.
can never escape you.
No. But there's a lot of them out there. So there's the big ones we're sitting on right now and so on. And then there's tons of tiny guys that are down to, a few hundred feet all the way up to, breaking the sea surface. And to map these features, you can imagine having a research vessel go out with a multi-beam system and sending acoustic signals down and making maps. And it turns out that's pretty slow on the planet. So folks have been suggesting we should map the entire ocean so we know everything. We should know the Earth as well if we do
Every
Mars and
seamount,
Venus.
every
and so
plate,
yeah,
everything.
map the whole thing. Well, it turns out you have to do it with a boat that moves 10 knots on a huge ocean. And the calculations are that this will take 20, 30 years of ship time at the cost of $20, $30 billion. And it doesn't really solve a particular problem. So the investment seems kind of way out there in terms of what you get back. Everybody would love to have this data set, but it's too expensive and it takes too long time. So the alternative method has been to try to use satellite data. And this is where things get a little crazy, because satellites cannot see through the ocean, just like we can't. We can only sense the bottom with acoustic signals. So satellites can sense acoustic signals. So what they do is they can measure the surface of the ocean, which is not flat. There's short wavelength noise that we call waves, tides and swells. But if you have a big seamount on the bottom of the seafloor, it represents mass. And mass gives rise to gravity. So the gravity over a seamount is actually slightly stronger. And we can feel
It's
it.
more mass.
But it's more mass, so there's a slightly stronger pull, and the seamount will pull on the water, and the water will pile up over the seamount. It's a little bump. And this bump could be 5, 6, 10, 15 feet tall over 300-400 miles. So you can't see it.
Yeah.
But a satellite who sends the radar pulse down and moves around the Earth can see these things.
Radar.
Radar
That's
pulse.
the technique?
Yes.
So the satellite sends radar down with a bounce.
Yes, it bounces off, and when it hits the Earth, it's several miles by several miles footprint. So it averages out all the noise waves and things like that, and it goes back up. So we measure that distance, and then we know where's the satellite, because the satellite gets tracked.
You know exactly where
So we
the
know
satellite-
exactly where it is, pretty small error. So we
Yeah.
can compute relative to an ellipsoidal Earth shape, ideal shape.
Yeah.
What are these bumps? Okay, so we're mapping the surface of the Earth, and that's called a geoid. It's where the water wants to flow, basically. So it flows uphill because the gravity pulling harder there. Now we can turn that geoid, and we can estimate what would the mass on the bottom of the seafloor have to be to create this pull and this shape on the surface.
The map under the
Yeah.
seamount.
So like if you have a bump on the sea surface due to gravity, the sea floor can't be flat, because then it makes no sense. So there has to be a bump down there of some size and magnitude, pull on the water to get that shape.
Yeah.
So we solve this problem of trying to compute what is the distribution of these mass anomalies on the sea surface.
So, but you can tell what's at the bottom by looking at the water on the top.
Yes. And that's the crazy part.
That's very interesting.
Yeah, so it's remote sensing. It's one aspect of remote
Remote
sensing.
sensing. Now, talk about radar, but radar usually is through water, not air, right? Is radar? I guess radar goes everywhere,
Yeah,
doesn't it?
yeah, we have ship radar measuring,
Do you have to have any special calculations to know when it's entering the water? Or
No,
it doesn't matter?
You're timing the pulse. So you send off the pulse, it bounces off and comes back, and you're basically measuring the time. And then there's all kinds of scientific and engineering expertise going into eliminating all the problems, like slow down in the ionosphere, moisture affects the
Sure,
propagation,
rain,
all kinds of stuff. So there's a lot of people who are very sophisticated dealing with this problem to make sure the data is as clean and calibrated as possible.
Yeah, one more thing is, what about hyperspectral imaging? I remember that you could see things like submarines
Yeah.
under the water
Yes.
using hyperspectral
You
imaging.
can.
Is that got an advantage on radar, or does radar have an advantage on that?
Well, I think they're used for different purposes. So the hyperspectral imaging can see a little bit, but it can't, because it's higher frequency, but it can't see very deep. So it can be used for mapping near shallow waters. But we're talking, many miles of deep oceans.
When you're looking down at the water on top of the seamount, that's miles down.
Yeah, the small seamounts will be, miles beneath the surface.
Yeah.
So there's a big range of depth. But yeah, we're looking at things on the deep sea floor that we can't see.
So one other thing about this is you mentioned that you're involved to a large degree in computer science and computing. And,
Yes.
And I guess that means getting the data from the satellites,
Yep.
which would be what, public domain. You have
Yeah,
no
it's
problem
public
getting
domain.
that.
Yeah.
Whoever the satellite is run by, including countries other than the United States, I guess.
Sure. Yeah, so interesting with this data set, it was initiated back in the Cold War days, in the 70s. And the purpose was the Navy needed to know the gravity field of the Earth at a very detailed scale, not just, what is here, what is it over there, but sort of what's the changes. Why? Well,
Yeah.
during the Cold War days, we had submarines with Polaris interballistic continental missiles to launch in case there was an attack. And those needed to know what is the vertical at that location, so they could set off the rocket in the right direction and hit the bad guys. Well, if there's a seamount right next to the submarine, that gravity is going to pull on the water, and it's going to change to what's vertical in that reference frame.
So your firing calculations would be thrown off.
Yeah, so now you're hitting Oslo, and that's not good, right?
Very bad,
Very
very
bad.
bad.
So the Navy initiated this program to launch satellites. It's called GeoSat.
Geostat.
GeoSat.
Sat.
Yeah, and it measured the sea surface, and they used that to calculate gravity, so they could measure these changes in the vertical. Scientists would love to get this data set, but it was classified. But then the Europeans started to do the same thing. The ERS satellites, 1 and 2, was launched in the late 80s, I believe. And so they were collecting the same data. And at some point, Congress, I think Al Gore actually was instrumental in this thing too, was able to push the Navy to release and declassify the data. So during the 90s, data was first classified from 60 south to 30 south, and then a few years later, they declassified the whole thing.
So you can get it from most places, most
Yeah.
countries, most
Absolutely.
satellite countries in the world.
Yeah, so now
Not
it's
North
public
Korea,
domain.
not North Korea.
Don't know about those guys. But you can Google, satellite, gravity, geoid,
Get it all.
and altimetry, and you get this thing.
So what does it look like when you get it?
Well, fortunately for me, there are people who have spent their life perfecting this process. So I have colleagues at Scripps, University of California, San Diego, Dave Sandvall, and Walter Smith, who works for NOAA. These are colleagues of mine. And they are specialists in taking this long-track satellite data and processing it into grids, images if you will, but grids where the data is equidistant in latitude and longitude, and this is the data they release. So they release several products. One is just the geoid, which is basically the shape of the sea surface. That one is
Which is a one-dimensional thing where you look at a certain geo position,
Yep.
and you find that the height of whatever
height
is
is a
there
bit-
is this high.
this high above the ellipsoid.
Two
is the
fields,
reference.
2 fields only. Where and how high?
Yeah, and then there's the gravity grid, which tells you the changes in the pull, the anomalies, so the difference in pull between the normal, what you expect from a spinning Earth, and what you actually measure. So it's a small anomaly. And then they do this calculation where they compute what is the sea surface, what's the ocean floor likely to look like to give rise to what they observed. And that's a topography map, basically, or a bathymetry map.
How fine is the data? Every yard, every meter,
No,
every
so
mile?
it's depending on a broad brush here. So as I said, the satellite footprint, by the time it hits the sea surface, it's several miles square.
Several miles.
Yeah. So that's sort of the repeat precision. And in terms of what can you see, you might see features that are just 5 to 10 kilometer long. You can see that they're there, but you're not getting the correct amplitude or the height. If they are in the 20 to 30 kilometer length scale, then you're starting to get more a truthful picture. So you can get the amplitude. But you can detect features that are there, you just can't measure the amplitude
No, so
correctly.
there's an algorithm that can measure the topography, the heat, whatever, out of those 2 fields. Amazing,
Yeah.
right? With
Yeah.
millions and millions of records for
Yes, yes.
every word takes the measurement.
Mhm.
But now you're into computer science.
Yes.
You get this data. You put it on a machine somewhere. Do you make those calculations? Do you run the algorithms that can tell us, what it is really saying?
Sometimes I refine what they have done for a smaller area to get the higher resolution image, for instance. But most of the time we are given these grids. They built up this expertise of processing over the last 30 years. So for me to redo exactly what they do, it will take time, not 30 years, because they published the routines and the algorithms and the theory, but one will have to spend a lot of effort to actually do it.
Okay.
And you probably wouldn't get funding for it because it's
done already.
It's done already. So,
Yeah.
so we're more users of this product than producers of it.
So
let's say.
what do you do with the work you get from these other guys?
Right. So, as I said, I'm looking for seamounts. So now we're looking for bumps of a certain shape and signature that I can identify as a seamount in the data on a global scale. So I've been writing algorithms that will detect these features in this data automatically. Because one thing to look at small images and
You're looking
count
for
them.
measurements that climb up to a
Yeah,
a
so you're
height
trying
and
to
have that
find
thing on the
an
top?
isolated, so the definition of a seamount is an isolated, not circular, but sort of isolated height,
Right.
separate from other
And
things.
usually it's round or oblong.
A round or elliptical oblate, something
Yeah.
like that. So, but it's not a ridge, for instance.
So your special software will take the other guy's
Data sets.
data
Yeah.
and look for a certain imprint,
Yeah.
and that would be the imprint of a seamount.
Yes, and then I would use what I find in studies of plate tectonics to try to understand how the plates have moved in the past. Use those as markers again to track the history of plates.
So now you're finding them, but how can you find the movement of a plate from making a map, say the Pacific,
Yeah.
of the seamounts, all the seamounts in the Pacific? How do you do that?
Yeah, so it's tricky because we have, let's say there's 10,000 seamounts that we can sort of discern in the Pacific with
Yeah.
the current technology. There's probably way more as they get smaller, but we can't really resolve the smallest ones.
Yeah.
So I have 10,000 seamounts. I don't know the age of these seamounts. There's no label saying
Yeah.
formed 100 million years ago, formed
Yeah.
yesterday. But we can sort of figure things out that seamounts that are formed very close to the mid-ocean ridge have to be very young because they can't be formed before the plate was formed. So that gives you a sort of an upper age, basically.
The plate forms them, so
Yeah,
they,
so the
they
plate-
could not exist
They
before
can't build
the
on
plate.
top of it
Yeah.
before there's a plate, right?
Yeah.
So that sort of limits how old they can be at any location. And then we can play games to say, okay, seamounts grow to a certain height, but only if the plate can support them. If they're too big, the plate will bend and the things will crumble. So what we find is
Is that
that
a bad thing if that happens?
it's bad if you're on them, yeah. So we had, for instance, the Hawaiian Islands, there's been a lot of landslides off them early
yeah,
in the
yeah.
history of the island.
Tsunamis?
That would have generated tsunamis too. Yeah. So we worry about things happening now. There's been talk about the south flank of the Big Island could fall into the ocean and we all be running
Any
up the Mountain
violent
Kilo.
act has a violent reaction.
Yes, right.
Okay.
So we worry about that, but one reason why the Hawaiian Islands are so big is that the plate we're sitting on is very old. It's 100 million years old. So it's cooled off for 100 million years. It's very thick and strong. It can handle that. It does bend, flex down beneath them, but it can handle it. Versus if you're very close to the mid-ocean ridge and the plate is young and weak and hot, it can't. So there seems
It
to
can
be
crack. It can.
yeah, it will just crumble and they will just fall
Yeah.
apart. So it seems to be some sort of correlation with size and age of the plate when it was built. So we can play games like that and assign ages to the various seamounts. Plus, there are seamounts we do have ages where people have gone on and dredged rocks, drill the seamount, and they collect the samples, take it to the lab,
Oh.
and measure using radioactive
Need a
decay.
autonomous vehicle to do that?
Would be nice, but no, it tend to be sort of, let's throw the old bucket overboard and drag it along the bottom. That's sort of
Really?
the,
Okay.
yeah, that or drilling. So
But the bottom could be miles down.
that's right. It gets
Okay.
kind of a fishing expedition at times. Because drilling is very, very expensive. You know, a drill ship like old companies use, that's basically what we kind of use for
Yeah.
drilling in a deep ocean. And it's expensive and time consuming, and you have to have a good justification.
So do you get a beat on actual movement from the data you have and the analysis you make?
The motion
Can
of
you
the
tell
plates,
me it's
yeah.
moving an inch a year or whatever?
Yeah. So we look at a very long time scale, obviously, let's say 100 million years. And we can look at indicators that show that the plate must have been over here during this time frame, and now it's over here in this time frame. And by just doing the basic math of dividing distance by time, we can come up with an average estimate of an inch per year or something like that.
How can you tell that it was over here, not here, 100 million years ago? They didn't have satellites then.
That's true, but we're so things that I've left out is that we have a good idea of the age of the seafloor everywhere, because
How do you get that?
yeah, so we have the Earth magnetic field, and it turns out it is not constant and it's not always pointing north. It flips sometimes to point south.
Really?
And this happens not super regularly, but let's say every million years.
Okay.
But sometimes it's stuck in one location for 20, 30 million years. We have a long period with very similar magnetic conditions.
But knowing that,
So
and
what-
knowing that it's changing,
Yes.
you can make some calculations.
Yeah, so we have the plate being formed at the mid-ocean ridge and moving to the side as new materials being formed. And you can think of this as a magnetic tape recorder. As the plate moves out, the new rock that are formed, they'll cool off. At some point, they cool below what they call the Curie temperature, and it freezes. And when the rock freezes, it records the orientation of the magnetic field, because it's magnetic minerals that have iron in them, and they align just like iron dust, will align with the magnetic field of the Earth. So that's frozen into the plate, and then the magnetic field flips for reasons that are difficult to understand. It will record a different field. So it's like a magnetic tape recorder where these things record on, off, or up, down.
Years at a time. Yeah.
Yeah, roughly, but it's not even like that.
That's gonna, it's gonna do something terrible to compasses in about a million years.
Well, if you watch the movie The Core, you'll see all the horrible things that can happen when the Earth flips. So,
Is that an accurate?
no,
No.
it's a Hollywood movie, but it's humorous.
So, what kind of conclusions do you make from all of this? In other words, are you publishing in scientific journals?
Yep.
What revelationary conclusions do you come to?
So we seem to find that the Pacific plate, which is one we're on, so we care about that. It's the biggest plate on the Earth, so we're number one, and it has moved more or less steadily west, northwest the last 50 million years or so. But at that time, before then, we used to think that it was moving north, more northerly, because the Emperor Seamount chains point more northerly. So the Hawaiian chains go like this, and then the Emperors go up here. But now there's a lot of data suggesting maybe this is not just reflecting past plate motion, but the plume that formed these seamounts may actually have been drifting a little bit due to a subduction zone that pulled it further north, and then it got released and it put south. So it gets more complicated now, so we have to worry about more moving parts, basically.
Yeah.
So I'm writing software to try to deal with these complexities to analyze.
You have to be so clever and realize that
I'm
whenever you come to a conclusion, then you find that no, there was an exception to that rule.
Oh, yeah, sure.
No, that something else was happening too.
Yes.
It's like a mystery novel.
I know.
Like CDI.
You're never done. So the thing is, it's a process, right? Science is a process of discovery. So
CSI. CSI.
Yeah, exactly. So the trick is to not get caught up in your particular hypothesis or your model, because they may be wrong. And you have to be willing to try to defend it, but when things are changing, you just, you reevaluate the model all the time.
Yeah,
You don't believe it, you just test it.
Yeah. So it's an ongoing.
It's an ongoing
thing. And so this, scientists, they come into a mainstream science for them.
Yep.
And they commit to it, and they work, they work all the angles on that science, try to push it forward, learn everything can be learned. This is your area, right? You're committed to this. This is your life work. We're talking
this is my
about.
hobby. I get
Hobby?
paid to have a
It's
hobby.
even better than a life work.
Yeah, we can't all be superstar sports person and make billions, but we can have a hobby as a job. And you have a hobby as a job in a sense. You enjoy what you do.
It's a hobby for me.
Yeah,
A labor of love.
Yeah, exactly. So, to me, it's no problem getting up on Sunday, going to work or something, because I'm curious that I want to get this done. So it really helps to have a hobby.
Well, that's fabulous. So what do you say to somebody who's going back to the kid who comes into your class, he may be in liberal arts, or he may be in science. What do you say to him about, your life as a model for his? What do you say to him in order to, grant him the mentorship that may take him down the same road? There's camera 2. It's waiting for you to give the
Very
message.
good. Well, I would, there's many things one can say. I would say, follow your dreams, try to do something different than what other people have done before you. It could be almost anything, but it's important to try. We all have to try to find something that we enjoy doing. You'd be much better off doing things you really enjoy than things you're told to do. And it may not always work out that way, but I think that's an important thing to try to follow. So in science, we always think that, we've solved all the problems now. But then comes the discovery last week of gravitational waves, and now we know something we didn't really know, and it took only 100 years after Einstein figured this out for us to prove it. So long time horizons, lots of stuff to do. We never know the results of this basic research, how it will change our life. It could be years from now, we'll be galactic discovery, right? We don't know.
Yeah.
So the fun thing with basic research is that there's all these unknown things. We'll learn new things about the Earth, the world around us, that no one has thought of before. And it probably, as we've seen in the past, it will probably pay off in applied applications later, but that's not why we're doing it. We're doing it because we love what we're doing and we want to learn more about the place we live.
Can I draw a parallel between what you do and what an astrophysicist does, an astronomer does, trying to figure out the secrets of the starry sky? Yeah.
Absolutely. Yeah, it's the same quest for discovery, whether it's on Earth looking at a microscope or looking through a telescope.
Yeah.
And because there's less trouble with the microscopes these days, but that's a separate issue.
Well, thank you so much, Paul.
you're
Paul
welcome.
Wessel, I
Thank you,
really
Jay.
appreciate you coming down.
That was
Professor at Geology and Geophysics at SOEST, and talking about research in Manoa detecting and understanding seamounts from space. Thank you so much.
You're welcome.
Aloha.
Thank you.
That's great.